Monte-Carlo Simulation? It's a analytical platform, or you can say mathematical tool or modeling technique for evaluating the reliability of a system considering all probabilities of system failure. Okay? So that means you are going to count all the randomness. That means occurrence of system failures. Done? So that is your ultimate job of Monte-Carlo simulation. Or you can say that these are the preliminary platform. If you see today's age 2024 context, so these are some of the mathematical tools. Those are used to lay the foundation of AI techniques. Okay? Now application can be even a game theory. Application can be to evaluate our system's availability or the evaluating the probability of system failure. So thereby it is equally useful in system design aspect. It is equally useful if you see, say for example, you want to do a stress and strain analysis of a semiconductor type or MEMS type sensor. Okay, that means that is designed at the nanometer or micron scale. Okay, it is equally applicable for generalized mechanical engineering studies where they want to evaluate or compare the stress and strain impact over a particular body, okay, under the dynamic conditions. So anyway, so here our job is to evaluate the system's availability or system reliability. So for that, Monte-Carlo simulation is one of the vital tool. Okay? So primarily you can say that it is purely a mathematical model. But what will be the advantage of this mathematical model? You can use this model to try out or to generate all probable samples. Okay? All probable type of samples in parallel that can cause a system failure. Okay? When we say system failure, so it is well known or well defined that you are going to evaluate these things for a stipulated period of time. Okay? So the time period you have to define. Within that particular time period, considering all possible randomness, you will be able to ensure the all possible reasons of system failures. Once it is done, so that means if whether you are in operation, whether you are in design phase, it is equally important. Whether you already ensure that okay, in my case fault avoidance technique may not be enough to ensure the 100% or nearly 100% availability of a system. So in that case you move to fault tolerance technique. When you apply the fault tolerance technique, then it will again help you to identify those places where you need to put a redundancy or standby. Okay? Even you have to introduce that. So that means if you are going to work out a system reliability aspect rather than being interested on the reliability of individual components, those are participating in that particular system. So Monte Carlo simulation is equally useful to evaluate the different probabilities aspects, system availability or system failure, before it comprises as a system, or once it is comprises as a system, that means it is installed or commissioned or the architecture is already developed as a system. Even after that, during the operation and maintenance period, you will be able to judge, okay, considering it says that all possible randomness. That means there is a probability of a malfunction also, okay, irrespective of whatever perfect mathematical modeling we have done, okay, whatever the necessary requirements we need to taken care at the design phase. Thereafter the product sets comes into the field or in market. So you are utilizing that particular product to perform an individual task at certain hierarchy, or you are using that particular component or a product or equipment to establish or commission a whole system where the role of individual components are already predefined, and in that case during the operation you wanted to avoid, okay, we said that avoid, yeah, there is not a, not a 0% probability of system failure or the 100% probability of system availability, but considering the all possible kind of randomness or all possible kind of malfunction that your system may experience during its operation phase, that is one. Number two, because the system is still in repairable conditions, okay, so during the maintenance period, what will be the minimum amount of time you will be needed to consider to avoid the possible system failure, certain possible system failure. This Monte-Carlo simulation is one of the useful tool. Okay? So you can say that it is one of the computational algorithm which is used to find or predict all the possible of randomness, okay, while you are going to pick the finite number of samples, okay, from that particular phenomenon. That means you are basically recovering the data. Okay? You are recovering the data. It is as good as that you are trying to evaluate the health indices of a particular system. So by evaluating the health indices, how will you be able to evaluate? You will be able to evaluate based on the certain system parameters of availability, or you consider the certain system parameters like MTTF and all, as far as the fault tree analysis is concerned. Okay? So on those cases, you will be able to predict the outcome of all those uncertain events, okay, and the possible chances to avoid it. Rest is all about the routine and all for executing this. So what can be the purposes? There are many, but maybe some of the countable things is understanding the uncertainty. Okay? So that means understanding the uncertainty means if I am able to know mathematically that what are the probable chances of malfunction, what are the probable place of troubleshooting if malfunction is already occurred, okay, or what are the probable chances of failure of a system after designing or after fixing its system architecture, okay, because you fix the system architecture of a model or of a system by taking care of all these design requirements. Okay? Still, nobody can say that the system is not going to experience any problem during its operation phase, or as and when it will go for maintenance, it will always require a minimum time of maintenance, or even during the maintenance, your maintenance skilled persons or highly skilled persons, they are not going to face any kind of trouble. Okay? So because of this, we can count all those uncertainties. If you know all those uncertainties, that means you can already develop a framework, okay, that will help you to come out from all those possible chances of uncertainties. Okay. If you can know the reason, okay, or if you can know the place, if you can know the time, if you can know the space where you are going to experience those uncertainties, those failures, so it is as good as that you can think of or you can prepare yourself to develop the necessary remedies. Okay. That is the purpose. Okay. Number two, estimate possible outcomes. Obviously, if you know it, so you can estimate all those outcomes to avoid all those uncertainties. But remember, in these cases, it is always necessary, or you can say compulsory, that the range should be always given. Okay? That means operation hour or maintenance hour, or how long your system has to perform, okay, without a rest or in active condition, active mode. These things you should be well known. Okay, it is as good as that your operational maintenance cycle should be well known. Then only it will work. Improving decision making capability, it is obvious. If you know the probability of the system failure, you can count the necessary remedies for that, okay, or the preparation to come out from those kind of uncertain situations to avoid those kind of failures. So it is obvious that in these cases it will always help you to improve the decision making capability. Enhanced risk management. Okay. Any doubt? Optimizing resource allocation. Okay, I know the reason that where it will be fail, probability of failure, what are the duration it can fail, what are the causes because of which your system can fail, and thereby now I am in condition. Okay, may not be 100%, but maybe around more than 90% time I will be already ready. Okay, with some standard practiced ready-made solutions, or you can say that trial and tested solutions, that if your system may experience three different kind of malfunctions. If it is experiencing malfunction type A, B, C, these are the solutions you need to replicate. Okay? So, on those cases, you will be able to optimize your resources. Okay? Optimize the resources means maybe some of the components you may require to keep always available in your store. Okay? So that the necessary replacement could have been done. Okay, because those components may not be repairable. That is number one. Okay. Number two, probably you are required to keep some of the components. There are n number of components participating, out of which m are very critical components, where m is far less than n. But for those n number of components, the wait time should not be, let's say, 1 hour or 2 hours, okay, or maybe few minutes. Okay, in industry practices, always it is normally in hours. Okay, so say for example, even if it is 2 hours, so there is no guarantee that where your plant is commissioned, okay, your nearby OEM will be able to provide those resources at your doorstep within 2 hours or within 1 hour of time, or maybe within 6 hours of time, or within a day. So in those cases, you have to keep the redundancy of those critical components in a standby mode, okay, in your warehouse, okay, or you can say that in your store where you can provide the necessary services. So that way you will be able to optimize the resource allocation. Okay. Core concept. So till now I hope that it should be clear that what you are going to Monte-Carlo simulation is going to do. So first of all, it is a computational mathematical algorithm, okay, that will help you to generate or evaluate all the possible kind of randomness to avoid the system failure. So this is the reason that you can say that it involves in the random inputs based on a specific probability distribution. Clear? The time range, or you can say that the duration of operation should be known, and at the same time the type of probability distribution function you have to consider that should be already prefixed. That is normally is prefixed. Okay? You know that you are in useful life period, okay, and the life cycle of each and every component that is participating is very high. So very high, that means the rate of change, that means the degradation in life or the degradation probability of failure, okay, with time is very low. So I can treat in those scenarios, I can treat that the rate of failure is extremely low. So therefore we consider it as constant failure rate, and therefore we can consider exponential distribution. Okay? Okay, but exponential distribution may not be valid in each and every case. Where you need to apply the binomial distribution, where you need to apply the variable distribution, these things are already prefixed. So that is what it means to say that for a specific probability distribution. Number two, very important thing is that multiple probability simulation. As I say that there are n number of possible chances or randomness or the possible reason of failures. So Monte-Carlo simulation will help you to evaluate all those possible chances of failure at the same time. That means you can run a parallel simulation. You can consider all those inputs parallelly to generate the possible outcomes, okay, based on the randomness of this particular material. Done? So that is the thing. So for example, if I give a small example of MEM simulation, say there is a system and you want to judge the differential pressure of that particular model. Okay? You can treat it assume that this range is some tens of mm, this dimension is also some tens of mm. Okay? Some millimeter to millimeter scale, or maybe some micron to millimeter scale. Depending. Normally microns is this depth. I mean what we call sensing layer. So that is in micron. Normally this dimension is in mm, some tens of mm. Okay? Now that is one architecture. Another architecture is to follow this parabolic pattern. Okay. Now tell me that, okay, so that is a two dimension. So that is one structure, that is another structure. Now your job is to evaluate the differential pressure at to the base address. Which model will help? One architecture is available, we use it. Okay? One can help you to evaluate the absolute pressure, very rare applications. One can help you to evaluate the typical relative pressure, and one can help you to get the differential pressure. So let's say I want to calculate differential pressure. Okay? And that subject or that object which I want to use as a sensing media, that dimension is in micron scale. Okay? So micron scale means it is very well clear that irrespective of my or your expertise, even you are highly skilled in that particular area, because of the dimensions limitation, my sensors are not in a correct position. My human sensors are not in correct position. Okay, to calibrate that particular device or to calculate, that means to receive the outcome of that particular device very well. So I will take the help of some kind of micro machining technology or some kind of automatic measurement mechanism or some kind of automation. Okay? So in those cases, two different structures are already provided. What you will do? बोलो भाई, क्वेश्चन इज क्लियर? Let me help you. Same structure. Depths are different. Okay. Positions are different. Structure is more or less not different. Differential pressure if you want, that means you need to calculate at least two pressure at the same time. Okay? And the difference of that. Done. Okay? So let's say that is some controlled with some controlled pressure. Okay? Right? So that means over the surface of this particular floor, so we can typically assume that if it is a controlled pressurized environment, so over the per unit area of the surface, the amount of pressure is imposed is typically equal. Whatever pressure is imposed in that point, the same pressure probably I can experience here, same pressure I can experience there. Getting my point? So assume that is that surface. It is some dimension, some finite dimension. Maybe in mm, but in some finite dimension. Mm means maybe if I will keep that particular sensor in the same group, as compared to this physical surface of that particular sensing material is going to experience more pressure. Why? Because space is less. So it will have a higher sensitivity, number one. Okay? But that is not our objective. My objective is to find that which particular solution will give me the most optimal condition. Not all. Stress and strain has a certain relations. Typically opposite. Agree? Where the stress is more, strain will be least, or strain is more, at that particular point stress will be less, for sure. Now my second job is that what is my application? So my application is to calculate the differential pressure, right? So I will not bother about the absolute pressure first of all, because it has nothing to do with that. Differential pressure, that means it is itself a relative term, because differential pressure can be calculated between the difference of 2 bar minus 1 bar. Differential pressure I can also calculate at the difference of 10 bar minus 8 bar. My reference will also change and my input will also change. The only thing is that I need to calculate the difference of the two, over the same controlled environment. Correct? So you need to decide that which particular portion of this particular surface, you need to create, whether this point or whether this point or whether this point, where the amount of strain and stress over the body will be exactly equal. Whatever. Definitely not in one direction, because if you will keep towards left, then the stress and strain equation will be imbalanced. Okay? So it's very obvious that I need to take at the microns level my dimension. If this is x distance, so this distance should be exactly x. Right now? Okay? So that within that particular limit I will be able to create this depth. Now what kind of junction it is? What kind of junction it is? Step or graded? We don't require to recall those device engineering. Simple thing. Sudden change or slow change? Think about it. Slow. What is the rate of change here? Very high or very low? Very high, na? That is infinite. Isn't it? This is infinite. I cannot do, so I will twist it, I will take little higher degree, but not infinite. That's all. So it's a very stiff change, na? So step change. I am walking here, suddenly at this point, I will reach to. So what is the rate of change? It's very high, isn't it? So what is it? It's a step change, okay? To take all the staircases, change is always sudden, right? So there is a step change. What is here? Slow change. If you are here, again the change is slow. So change is very slow. Not is also random, but it's very precisely designed to show. Understand? So now I want to calculate differential pressure. Tell me which one will be easy. If the difference of these two will be a stiff change or very slow rate of change. Very slow rate of change. Sudden change. Understand? Because in that case what happened? That at this particular point you are getting certain pressure, let's say P1. Okay? So here you are getting pressure P1 at this point. But due to this high rate of change, now here you will get some other pressure P2 at the same time. Okay? So when certain pressure is applied over this entire body, impact of the pressure over this point and this point will be very different. So therefore your electrodes will give you the differential pressure, the difference of the two, because it is experiencing both the pressure. So what output it will give you? Difference of the two, because both are the measured value. Now I am not bothering that P1 is higher or P2 is higher. In any case, you will get that absolute difference. Getting my point? Okay? On the other hand, you want a slow change, a relative pressure. Yeah? So then adopt the different values. So for these cases, when you want to apply those stress and strain analysis at the micron level, you can, that is one of the applications. Okay? the fabrication teams or these kind of sensors or signal conditioning, microelectronics, micromachining people, VLSI design engineers, mechanical engineering, mechatronics. These people again also use this. Okay? We can also use it as far as my plant is on a running mode. There I can also use for system failure or systems availability analysis. I am not bothering about these individual components. I want to ensure that in any case my system should be available with the highest possible availability rate or during the active mode. Okay? Irrespective of possible chances of malfunction during the operation mode, possible chances of randomness while the subject is in the maintenance period, because when it comes to maintenance it has a scheduled cycle. Let's say its maintenance period is that the component will be well maintained and be in position to be reused within 48 hours. Now that 48 hours is actually average period. Okay, some of the same component may be maintained within 24 hours and some of the component maybe it will take 7 days. Okay, because of some catastrophic failure. Okay, that is something is not repairable. To evaluate all those things, that is what we call multiple probability simulations. Now all these possible simulations you can conduct at the same point of time. Two examples I have given you. One is related to system, another is related to the component. I hope that this should be clear. Okay, lot of things would have been repeated. Okay, so that is good thing for the reliability engineering. Okay, you can apply the knowledge of module 1 and 2 here. Applications. Okay, as I said that if you want to compare it with the today's context, not unlike 15 years back, the role of AI and all these things was typically on paper. Okay, there was no thinking of the quantum computers, there was no thinking of applying the AI on a real-time basis. Applying the AI or AI based techniques, or I would say broadly the machine learning techniques for some kind of simulation, some kind of analysis purpose, that was there 1 or 2 decades back or even 15 years back. But unlike the current age scenario, nobody was thinking at that point of time to apply on a hardware or to develop some kind of formula. But okay, this is one of the platforms, okay, that helps to lay the foundation. That is the purpose. Why? Because it has a capability to model the all different possible kind of objectives. Objective means the number of reasons why your system can fail, or the number of reasons to ensure that irrespective of all this possible malfunction, how can I ensure that my system should be still available in the useful time period or in the useful active mode. Okay, so that is one of the reasons that it can use for these kind of dynamic modeling purpose. Okay, risk assessment, optimization, obviously these are the different applications. Then finance, stock, self forecasting, project management, okay, pricing assessment, risk assessment. These things obviously normally you can say that the typical management guys they use. Okay, that is also equally important platform. Advantages. So obviously you can predict certain advantages. If I will be in position to calculate the all possible chances of randomness, if I will be in position to know well in advance about the probability of a system failure during either in the active mode means during the operation period, or during in the its inactive mode, that means in its maintenance period. So all those scenarios I will be able to correlate those things. I can conduct those sensitivity analysis. I can go for a long-term predictions, because obviously that will help me. Okay, if I know all possible chances of failure. Okay, so for the predictive models, okay, it has a certain advantages. Predictive models with fixed input. Fixed input means who is providing the inputs? You are in a manufacturing mill. Your job is to produce a specific kind of products, okay, in a continuous fashion. How long? For a definite period of time, until your order is completely executed, okay? Because your one team has booked the order, and accordingly the skilled part, the engineering part, or those expertise who are in field, they are ensuring to produce the same number of pieces, okay, to execute your order. So in those cases, if I know that what are the possible chances of failure or what are the number of predictions, okay, to take care of all the availability of a system, that means I can go for a long term planning, okay, that even there is a chances of failure, how to overcome from this situation. If the number of orders are very high, okay, so what are the plans I need to execute to optimize the assembly line efficiency, okay, so that it can ensure to the higher availability of my products. Even catastrophic chances of failure, even chances of malfunction my system can experience, okay. So obviously if at one stage if my fault avoidance technique will not be good enough, okay, irrespective of very high probability, then I will jump to the fault tolerance, okay, plan for some required standby, even it will cost me very high, but with the help of that we will already discuss somewhere in module 2 or 3 that I can ensure the higher availability of my supply chain, okay, and thereby it can also help me to reduce my operational cost, it can help me to reduce my operation and maintenance cost, which is one of the major factors of the product cost, okay. So all these things you will be able to done. Any doubt? So in next class we will discuss, if you want go through these materials or on your book, okay, we will discuss that how this Monte-Carlo simulation platform works. Okay. Done. You can take of like softwares like Real software, that is one of the platform, very old platform, like 20 years back. It's specially designed for these purposes. You can take the help of MATLAB Simulink also, Simulink platform also, but if you want to do certain kind of practice, not mandatory from subject point of view, but for better understanding. Done? Over. Thank you.